Yes, class. So in your magnetics lessons, we'll start with Biot-Savart's law. So in Biot-Savart's law, firstly, you have magnetic field's magnitude. So magnetic field's magnitude is directly proportional to current. It is directly proportional to current element, directly proportional to sine theta, and inversely proportional to 1 by r. Now, see, what is the theta over here? It's the separate. It's actually the distance between position vector and the current element. Position vector is simply the separation of the point from the conductor, and current element is a part of the entire conductor that we take. So when you combine this, you get dB is directly proportional to ideal sine theta by r square, right? So dB is written as k ideal sine theta by r square. Now the value of k here in magnetics, this is mu naught by 4 pi, that is 10 to the power minus 7. Mu naught by 4 pi, that is 10 to the power minus 7. This is one conversion. 1 Tesla is equal to 10 to the power 4 Gauss, because Gauss is the SI unit of it. Now, this is permeability of medium, permeability of free space. This is exactly like permittivity that governs the magnetic field with respect to medium. For different media, you have different values of permeability. All right, so mu r is equal to mu divided by mu naught. So mu is permeability in any medium, and mu naught is permeability in air or free space. Now, direction of magnetic field. There are two methods by which we can find out the direction of magnetic field. One is if you hold the wire in the right hand and your thumb is pointing in the direction of the current. Then the rest of the curvature of the fingers at that particular point, if it's going outwards, that will be magnetic field outwards. If they are pointing inwards, that will be magnetic field pointing inwards. And second method says that you have to place your fingers in the direction of current. You have to curl your fingers towards the position vector. The thumb will give you the direction of the magnetic field. So this is about Biot-Savart's law's formula. Now you have certain applications from Biot-Savart's. It is given due to straight wire, magnetic field due to circular wire. So see, straight wire can be finite, infinite, semi-infinite, and circular wire can be circle, semicircle, an arc of random angles subtended, right? So see, for straight line, you have finite, infinite, and semi-infinite. So for all these, you have one specific formula by which you place it, and derivation is not part of your syllabus for straight lines. So remember, for infinitely line directly, mu naught by 2 pi r. This is it for infinitely long wire. Infinitely long wire means infinite from both the ends. Both the ends are reaching towards infinity. And then you have semi-infinite wire, mu naught I divided by 4 pi r. So accordingly, you will apply the rules. Then you have magnetic field for a circle. For a circle, the magnetic field is mu naught I divided by 2r. And magnetic field for a semicircle is mu naught I divided by 4r. Right? Mu naught I divided by 2r is for circle, and mu naught I divided by 4r is for semicircle. And if you have a circular arc which is subtending some angle theta, this angle alpha, let's say this is unknown to you. So you will write it as mu naught I alpha divided by 4 pi r. So here it's written circle mu naught I by 2r, semicircle mu naught I by 4r, and for any angle subtended mu naught I alpha by 4 pi r. Nextly, you have Ampere's circuital law. So Ampere's circuital law is a very small law, and that can be asked to you to write in the paper class. This law part, not this writing part, this is asked to you. So according to Ampere's circuital law, line integral of magnetic field along a closed loop. This is mu naught times the total current enclosed by the loop. It is very similar to Gauss law. It's like the magnetic version of Gauss law. In Gauss law, you had no phi is equal to whatever E dot ds was, phi, that was equal to 1 over epsilon naught times the total charge enclosed. Here, what is happening in Ampere's circuital law? The line integral of magnetic field. What is meant by line integral of magnetic field? B dot dl. This is equal to mu naught times the current enclosed. Then under the applications of Ampere circuit law, you have two devices. One is a solenoid, that is windings of copper wire, and when both the ends are tied together in the form of circle, that is solenoid is drawn into a circle, we call it as a toroid. So formula for both solenoid and toroid remains same, that is magnetic field is equal to mu naught Ni, but the value of N will be different. For solenoid, you will have number of turns per unit length, that is N by L. That will be for solenoid, and toroid will be number of turns per unit length. So length of a circle will become 2 pi r here in this case. So mu naught Ni will become N divided by 2 pi r. So solenoid is mu naught Ni, where N is small n's value is N by L, and value of toroid is B is equal to mu naught Ni, and value of N is N by 2 pi r. So these are the two devices that you have, solenoid and toroid. Then you have magnetic Lorentz force. Magnetic Lorentz force, firstly you have magnetic force. So magnetic force simply says that it's the charge multiplied by the product of velocity, cross product of velocity and magnitude. That is your magnetic force. And because of electric field, you have electric force, that says charge multiplied by electric field. This is the formula for electric force, and you have the formula for electric magnetic force. So if a charge is kept in electric field, you will just use the formula QE. If a charge is kept in magnetic field, you will use the formula QP cross P. So when you will add both the forces, you will get QE plus V cross P. This is known as Lorentz force. Fine. So direction of electric field is given by the individual electric field's direction. Like for positive charges, you move towards; for negative charges, you reverse the direction. And magnetic field, same thing. The way you use right hand rule, using your right hand rule. Next, you have before magnetic dipole, you have force between two parallel wires. So force between individual wires is actually given by BIL. BIL, I, B cross L. This is actually the formula for it. So if it is a single conductor, you will use BIL sine theta. But if two parallel wires are kept together, then the force is given by mu naught I1 I2 L by 2 pi d. Now when you shift this L in the denominator of force on the left hand side, so force per unit length, this will become mu naught I1 I2 divided by 2 pi r, right? So this is the formula. Is if the formula comes to write force per unit length, if you will see Newton per meter in your answer, so this becomes the formula for it. If you see just the force between two parallel conductors, it is mu naught I1 I2 L by 2 pi d. That's it. This is it. One more thing. If the two conductors, they are in same direction, they'll attract, that is, they will be moving towards each other. And if they are in opposite direction, the conductors will repel. They'll move in opposite directions. Next, you have magnetic dipole moment. Magnetic dipole moment is the product of area and current. Area multiplied by current is known as magnetic dipole. So magnetic dipole, the way you have the electric dipole moment, you have magnetic dipole moment as well. So magnetic dipole is A into I, current area multiplied by current. So this is a technique to remember for south and north. Just to drop an S, put the arrows, mark the arrows at the edges. The directions of arrows will give you the direction of current for this particular polarity. Same way for north, you drop a north, you drop an N at the edges or the arrows of it, terminals of it, mark an arrow. You'll notice whatever is the direction of this N, that is exactly the same direction of the current. So this is how to find current in the current carrying coil, and write down the magnetic dipole for the current carrying coil. Then you have formula of torque. Torques have few formula. The derivation of torque is very important, class. So formula of torque is M cross B, that is magnetic moment into magnetic field, or you can write magnetic moment into area into current. area into current, right? So that becomes AIB sine theta. Instead, if there are more than single turn, you can write it as NAIB sine theta, NAIB sine theta. That is the formula of torque, NAIB sine theta. So M cross B or NAIB sine theta. All right, this is the formula for it. Torque, you just have this basic formula. From this only questions do come. Then you have conversion of galvanometer into voltmeter, voltmeter into galvanometer. Galvanometer into ammeter. Before that, you have the concept of moving coil galvanometer. See, it's a device which is used to detect current. So if you have connected galvanometer in your circuit and the current is flowing, so there will be deflection shown in the galvanometer. So what is the principle behind it? That a current carrying coil, whenever it is placed in magnetic field, it experiences a torque. And that torque rotates the coil and produces angular deflection. It rotates the coil and produces angular deflection. This is how the construction is made. Two magnets are kept. They are carved, and these concavities, they provide the radial magnetic fields. So magnetic fields have radial direction here. Then a pointer is kept, which is attached to spring with the help of wires. Copper wires are there on the soft iron core. From the spring, you can see a pointer is there that is pointing towards a scale. So scale has markings, readings, but no need to go into details of reading, because in galvanometer, main purpose is to detect current. You have to detect the current. Once detection of current is done, then the purpose is solved. So here deflections formula is NAIB by K. That is number of turns into area of the coil into the current into magnetic field divided by the torsion constant. And this theta is the deflection over here. Now sensitivity of the galvanometer. Sensitivity of the galvanometer, this means, see, how for a very small current, how much deflection is it showing? So if it is deflection per unit current, we call it as current sensitivity. If it is deflection per unit voltage, we'll say it is voltage sensitivity. So formula of current sensitivity is NAB by K, and formula for voltage sensitivity is NAB by KR. This is what is meant by sensitivity and the two formulas for it. Now, when you're converting a galvanometer into an ammeter, you will connect a very low valued resistor in parallel. And that device, now it is known as shunt. So what is the formula for shunt? It is Ig, that is the current passing through the galvanometer, multiplied by the resistance of the galvanometer, divided by I minus Ig, that is current minus current through the galvanometer. So a shunt is a low resistance which is connected in parallel with galvanometer to protect it from strong current. Next, to convert galvanometer into voltmeter, you connect a high series resistor, a high valued resistance in series. The formula for resistance here becomes voltage required divided by the current through the galvanometer minus the resistance to the galvanometer. So these are all the topics that are included in your magnetics, magnetic effects of electric current. Let's practice some questions from this topic, from this lesson actually, because this is more important than your next lesson. Okay, that is 5th lesson. So give me 2 minutes. Let me share the questions with you. You'll try it yourself. Then we'll discuss. Wherever you're having any doubts, let me know. Otherwise, share your answers. Whatever answer you're getting, share it in the chat box. See class, the solution for this question. Number of turns are 100 here. Number of turns are 100. A is how much? 20 centimeters, right? So let's convert it directly here only. That will become 0.2 meters. Next, what you have? 100 turns, 20 lies in xy plane with its center at origin of the coordinates. So z-axis, this point is at z, x, y, z. So you will write z as 0.2 root 3 meters. We have converted 20 centimeters again into root 3. And the value of current is given 2 by pi amperes. Now see magnetic field at the axial point if you have to calculate, because you have to calculate, no, find the magnetic field at a point at this only. So this is at the axis of it, xy plane's axis will be perpendicular, axis will be z. So magnetic field, this becomes mu naught NIA whole square divided by 2 a square plus z square to the power 3 by 2. So put in the values. This will become 4 pi into 10 to the power minus 7 n 100 I 2 by pi a square 0.2 whole square. This divided by, let me write pi in the denominator then directly. Then we have 2 into 0.2 whole square plus 0.2 root 3 whole square to the power root 3 by 2, not root 3 by 2, just 3 by 2 to the power 3 by 2. And here we have the pi. So when you solve this, this will become 4 into 10 to the power minus 5 into 0.04 divided by, this part will remain 0.2 whole cube. Then if you take common 0.2 here, 1 will remain. And what else will remain? Root 3 square will become 3 to the power 3 by 2. That's how you'll solve the denominator. So see how to solve it further. 4 into 0.04, this will become 16, 0.16 into 10 to the power minus 5 divided by, this will be 2 into 0.008 into 8, this much of Tesla. So this will become 1 by 8 into 10 to the power minus 4 Tesla. So this will be equal to 25 micro Tesla. That's how you'll solve the denominator step by step. All right, class. See, solution for this. Number of turns per unit length we'll have to find first because this is solenoid, as I've told you. So number of turns per unit length. This becomes 500 by 0.5. That will be 1000. 1000 turns per meter. Now formula is B is equal to mu naught Ni. Now look here, if B is equal to mu naught Ni, formula when you'll put it, L we have to find out, no? What do we have to find? Current. Okay, current. I we have to find out. So from here, if you put I will be equal to B divided by mu naught N. So magnetic field is 2.52 into 10 to the power minus 3. Mu naught is 4 pi into 10 to the power minus 7. And N is 1000. So this will be, let me check the answer. This will come out to be exact 2 amperes. Please cross check and see whether it's 2 ampere coming or not. An ammeter of resistance 0.8 ohm can measure currents up to 1 ampere. What must be shunt resistance to enable the ammeter to measure currents up to 5 ampere? See, total current that it can measure is 5 amperes, right? So total shunt resistance that is required, or let me write GS only. Shunt resistance that is required, this will be Ig by I minus Ig. So multiplied by G, right? This is the formula for it. So 1 divided by I minus Ig. This will become 5 minus 1 multiplied by what is the resistance of galvanometer given? 0.8. So 0.8. So it will be 0.8 by 4. This will become 0.2 ohms. Second part says what is the combined resistance? See, resistance of ammeter, this is given by normal parallel connection. So that becomes 1 by resistance of galvanometer plus 1 by resistance of shunt. So this becomes 1 by 0.8 plus 1 by 0.2. So this will become 1 plus 4 divided by 0.8. This becomes 25 by 4. So equivalent resistance will be 4 by 25. That is 0.16 ohms. What is the force on a wire of length 4 centimeters that is placed inside a solenoid near its center, making an angle of 60 degree with its axis? The wire carries a current of 12 ampere and the magnetic field due to the solenoid has a magnitude of 0.25 Tesla. So you will use the formula F is equal to I L B sine theta. Fine. So here theta is given as 60 degree. Theta is given as 60 degree. Current is 12 amperes. Magnetic field is 0.25 Tesla. And length is given how much? 4 centimeters. So that will become 0.04 meters. So when you'll put all the formulas together, force will become 12 into 0.25 into 0.04 into sine 60 degree. So this will come out to be 0.1 Newton. Now I think we have practiced lots of questions from magnetic effects of electric current. Now we'll practice questions from magnetism and matter, chapter 5th. Two small magnets are placed horizontally perpendicular to the magnetic meridian. Their north poles are at 30 centimeter east and 20 centimeter west, as I have drawn it in the figure from a compass needle. Now, if the compass needle remains undeflected, you have to compare the magnetic moments of the magnets. See, the compass needle at this point, lies on the axial line of the two magnets. When will it remain undeflected? It will remain undeflected when both the magnetic fields are equal. B1 is equal to B2. So this becomes mu naught 2 M1 by 4 pi R1 cube. This is equal to mu naught 2 M2 divided by 4 pi R2 whole cube. So from this only M1 by M2 will be left. That will become R1 by R2 whole cube. This is equal to 20 by 30 whole cube. That is 8 by 27. So ratio will be 8:27.